Testing 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19.
Okay, we need Wing. Wing, you're on. I think we need to start right away.
Put this right around here.
Oh, the previous speakers didn't do that, but they spoke hopefully in the microphone. But
They were putting it everywhere, and I kind of just try to make it work. I have a little bit of control over there of how sensitive the mic is.
okay. Okay, people, thanks for coming back on time after the break, and we are going to resume with a talk about Granula, performance monitoring tool developed at TU Delft, and Wing is going to present it.
Sure. Do I have the pointer for the PowerPoint?
A pointer. Do we have a...
This one?
Yeah, I think so. Yeah.
All right, we will start earlier. So my name is Wing Nong Ai. I'm working in the Free University of Amsterdam at a large research group under supervision from Professor Alexandru Iosub. So the topic I will present today is granular, is fine-grained performance evaluation of large-scale graph processing systems. So, well, large-scale graph processing. So, well, nowadays that our society is generating a lot of graph data that is not uncommon to work with a graph that is with billions of fetters and edges. And in the future, we will be working towards graph with trillions of edges. I believe you saw this multiple times today, so it must be true. So there is a set of specialized big data platform that is used to conduct full graph analysis on this kind of graph. And the performance of these systems are very crucial at this scale. And that's why we conduct performance evaluations on this kind of systems to understand the performance. We want to quantify the performance. We want to be able to explain the difference. We want to be able to identify the overhead and the bottleneck of the system and to recommend improvements. So our group and also many other studies has previously published a performance study on graph processing systems. One of the issues that we encounter is that it is very difficult to reuse the results of these studies. So the first issue is that many of these studies consider this system as a black box, that you give some inputs and then you measure the outputs, and then that is, so we don't really understand what is happening inside, despite that we can quantify the performance. And other issue is that it is very inefficient to perform fine-grained evaluation due to the complexity of the platforms and the complexity of the distributed environment underneath. So the issue here is that we don't have an end-to-end process to conduct performance evaluation, which means that analyst has to repeat a lot of boring work every time. Okay, there's a timer. So what we want to do is that to see if we can do better. So whether if we can improve the efficiency and the quality of performance analysis. We want it to be comprehensive, standardized, incremental, and automatable. So I will present this concept more in the coming slides. So granular consists of 4 main modulars, which is what we identify as the key elements in performance evaluation. It starts with a modeling, which encapsulates the concepts of a system. And we use this to actually gather the accurate performance data via monitoring. And then we use this data to create a performance archive such that it can be easily queried and reused by other analysts. And finally, we want to visualize them so that we have intuition what's happening. So what we try to argue is that only the modeling part is a conceptual challenge that is different for each platform, while all the other parts are just repeatable technical tasks that it should be all automated. So the key is actually the modeling part, which we will use a modeling to define a generic modeling language that is applicable to many different types of big data systems. A job here is being recursively defined as a tree of operations, and each operation is defined as an actor executing a special mission. So the user can actually focus on each problematic part, each operation, to see that there is a list of performance data that they can analyze on that is characterize the performance of the operation. So to show you example what we can do here. So the first step of using this granular tool is to build a performance model. And so what you can see here is a giraffe. And if you on the first level, you can see giraffe you can analyze a giraffe job as a black box. And if you go one level deeper in the domain, for example, what we're here for today is graph processing, then you can see very often there is a startup phase, and then if there's a low graph phase because most systems are in memory. There's a process graph that is where the system executes the algorithms, and offload graph that to return the results. And surprisingly, some systems doesn't do that because they are some rare prototype. And finally, there is a cleanup phase to just clean up the environment where you execute your job. And to go deeper, you can go to system level to see how each system implement this domain level operation. And you can go also deeper to where the actual performance problem is. So what can we see here? Well, for example, if we compare giraffe and power graph, then this on the domain level, you can see that they are actually very similar in structure, but for giraffe, for the setup, input, output, and processing time, they are all significant in the runtime. But for power graph, you can see the low graph is the issue. Therefore, we can actually identify performance issues in where are the performance issues in which step. And so this is, and so we can also further to try that that is where we can ask questions. Where are the problems? And to continue this is to actually verify that is indeed what we expect to see for example, the aggregated CPU time of each step. For power graph, for example, you can see that in the low graph there is only one core is active trying to load the graph, and that's why it takes so much time. So instead of guessing, we can actually we want some real empirical data to support our hypothesis. If you go back to, for example, the process graph stage of a giraffe, you can see that there are multiple workers trying to execute a list of super steps. And in each super step, you can see that it can either do some computation or they are inactive, just pending for other to finish. And you can see in each super step there are overheads, and there are also imbalance among workers. Actually, the imbalance is not always uniform. That actually is different per super step. So using granular, we can actually see what is happening. Have a better insight of what's happening. So finally, for example, we can use this to diagnose failure. Well, job failure is very common in big data systems, where, for example, for graph processing, it's very common to go out of memory and then job just die. But it's not always the case. Sometimes you can, basically what you would expect is that this will happen during the process graph phase where the algorithm executes. But for example, you can see when we are inspecting the performance of a power graph in this stage, that it actually happened during the offload graph phase. That doesn't make any sense. So what actually happened is that the implementation of this algorithm tried to push too many data back to the master nodes so that it can have the results. But apparently that is very stupid. You go the so yeah. Well, what happened is that you go out, the swap is full, and then the job dies. But you just see it go off memory, and you think that is the algorithm, but it's not. So here we actually have a better idea what is happening. So with this, we come to the conclusion that present granular as a fine-grained performance analysis systems for big data platforms that facilitate monitoring, modeling, archiving, and visualizations. We have 20 seconds for questions.
No. You have 1 more minute. Thank you, Wing. This time that you see there, that is actually leaving 1 minute left, 1 minute for questions. So, but yeah, you stopped in time, so now we can ask a question.
So I noticed that you said PowerGraph does single-threaded loading. Did you try doing that by splitting up the file into multiple threads? Because I've had a different experience.
One of the, this was supposed to be done, but sometimes the thing is that you don't actually know what happened if you just look at the overall time of the entire job. And there are so many configurations that you can apply, which sometimes you just skip your mind of what's happening. So this is just a visualization of show that that is a mistake when whoever who implement this function has misimplemented or misused the platforms. So I hope that answer your question.
Yeah, well, I will ask one. I will let one more question be asked. While I would like to request Matthias Haug, I suppose, or at least the presenter of Can Modern Graph Processing Engines Run Concurrent Queries, to come forward. Yeah. Who's that? You. Yeah, you are next. So please come forward. Oh, I'm so sorry. I'm looking wrong. I'm really so. I understand your bafflement, but this is. I'm looking for Martin Junghans actually. Sorry. Now your heart rate has gone up terribly. Meanwhile, I will give the microphone to Eyal with a question for me.
So what you were describing is a sort of a profiling framework for graph processing systems. Have you looked into more general purpose profiling frameworks and whether they can offer similar functionality?
Okay, if you talk about profiling, that is that probably you are measuring functions that operate in really fast magnitude that is like maybe millions in just 10 seconds. So, the idea here is that you should be able to first identify which part of the system is problematic, and then when you go deeper into that specific operation, then you want to profile that part, because that is where all this uniform function is being executed, and you want to really focus on that part and to get the performance of that. So that will be my answer.
Okay. Apologies again. So yeah. Thank you, Wing. Let's give him a hand for Granular. And now, yeah, indeed, the next presentation, which is on Gradoop. It's part of the Gradoop project.
No, it's supposed to be PGX.
It is.
Grade 17. It's on the desktop.
Am I again mistaken?
Where's the mouse?
Well, according to my schedule,
Well, that's fine.
not, but...
We were going off the one online.
Yeah.
Oh, okay. I'm still looking at the not reloaded pair, sorry.
May I?
Yeah, you can.
Hey, I'm Nicholas Roth. You might have guessed that my talk today has to do with graphs. It does, given where it is. Today I'll be introducing PGXD Async, an engine for distributed graph pattern matching. I'm not introducing a product, but I do have to show this. You might want to know this. This is just what I'm going to go over, motivate you. Then I'm going to describe the engine we use a little bit. Then I'm going to show you our nice results, numbers, and I will kind of wrap things up. So this is a graph workshop. I don't think I really need to go into the details about pattern matching, but just to make sure we're on the same page, let me define the problem of subgraph isomorphism in a single slide. This is a simple pattern we might want to match. In practice, there are usually constraints on the properties of these vertices and the edges, and usually this query graph we see here might be a lot more complex. But in this case, it's just an illustration. And on the right, in red, you can see the subgraphs that match this query graph. Those are what our engine identifies. So often, graph pattern matching is implemented with joins in a traditional database management system or as breadth-first traversal. Join implementations are sometimes not well executed because their primary goal is often to adapt existing systems to deal with graphs. They don't take advantage of index-free adjacency that's inherent to graph data, which can make them slower. Breadth-first traversal is an accepted technique for efficient graph pattern matching, but all instances of each vertex in the query graph are matched before continuing to the next step. So match all A, match all B, match all C. When this set of intermediate matches, which don't necessarily contribute to the final results of the query, don't fit in memory, breadth-first traversal isn't a feasible computation strategy. There are other solutions better than these naive approaches. If you look at the related works in my paper, you'll find systems that are asynchronous, that can handle lots of intermediate results, and that don't have communication in the critical path, but usually it's just one or two of these, and often they're tuned for RDF data model as opposed to property graphs, which are what our bread and butter is. So my solution to pattern matching in a property graph distributed across multiple machines focuses on asynchrony and strict, precise flow control to put an upper bound on memory consumption, guarantee the query runs to completion every time, and provide a high degree of parallelism. So how does this work? And the most important thing is that when we ask a question, we get an answer. It's easy to take this for granted, especially with modern technology, but there are no answers when your system runs out of memory or hangs in a deadlock, and BFT and even some of these join-based algorithms are prone to those. Depth-first traversal lets us store the intermediate results as a part of a thread state, pushing that as we move deeper into the graph and popping it back as recursive traversals return. This is a fixed amount of memory directly related to the number of threads active in a computation. Depth-first traversal also benefits from parallelism by being able to run all of the stages of the computation at the same time. So as one part of the computation might not utilize the full resources of a system, eventually data that's output from that part will fill the load in on the other machines. The next most important thing is making sure we have enough memory to receive computations from any machine at any of the stages. This paper describes these machines in more detail. I suggest you read the paper, but I'll tell you now that it has to do with flow control. So remember this pattern. In the next slide, we'll use it to illustrate depth-first traversal. Depth-first traversal prevents intermediate results from accumulating beyond our capacity to store them. Combined with intelligent flow control, we show that this can deterministically regulate memory consumption without significantly impacting performance. For example, in the data graph shown here, our DFT implementation would follow the printed matching order. And do you see the numbers there? That's the order I'm talking about. With an asynchronous implementation, we can work on the whole query at once as work arrives. When a computation needs data from another machine, as we see in this case, it just sends it off and then it continues doing something else. Either previous work or a computation received from another machine. Or, so in this case, the machine wasn't doing anything, so it just said, okay, well, let's work on that message. This is a very preliminary evaluation showing how selected queries from the 8 million scale BSBM e-commerce benchmark scale in PGXD async, our system. Larger queries tend to scale the best. You'll notice that P8 and P9 show very erratic behavior, and to a lesser extent so does P1. These are the queries that touch the least data. But the queries that touch a lot of data, for instance P4, all scale very well. See this spike from 1 to 2 machines? So one machine is our old PGX runtime. It's what we usually use. 2 machines is 2 machines in the distributed runtime, and because we partition our graphs randomly, you see this huge spike in time from having to go from everything contained in a single machine to suddenly having to do all sorts of information exchange. But that's quickly amortized by the additional computational resources that we get from tying in those additional machines. And also, it's often not really practical to fit everything in a single machine, especially when we're dealing with petabyte scale data. I hope you're convinced that the asynchronous DFT approach offers several advantages over others in a distributed environment. Full asynchrony and the idea of moving computations instead of just doing requests for the data allows for parallelism and good performance even in badly balanced or partitioned workloads. I mean, we saw random partitioning just over there. It scales to larger queries because it can't run out of memory from an explosion of intermediate state like BFT-based implementations. And even for the smaller queries, the key tends to be optimizing the code so that there's less of the constant overhead rather than a fundamental flaw in the design. In our paper, you'll find more details about what you saw earlier in the presentation and some design decisions and facets that didn't even come up here. If this interests you at all, I suggest you read our paper, and I also highly encourage you to talk to me in the poster session following this. I'm right by one of the main doors. Anyway, I hope you've enjoyed the presentation.
Thank you,
Any
Nicholas.
questions? I'll be happy to take them now.
Thanks, Nicholas. So, are there questions? there is a question.
How do you deal with cycles when you do the DFT?
How do we handle cycles? Is that your question? So that's the thing. When we're trying to match the pattern, if the pattern says there should be a cycle, then of course we go that route. But otherwise, if we detect a self-edge, we don't actually necessarily traverse that for more than once, because each edge matched has to satisfy some sort of a filter. And we only go a certain number of hops outside of the main graph. It's determined by the query plan. So sure, you might go around a loop 6 times if you have a very generic subgraph you're trying to match, and this would be homomorphism, not isomorphism. But in general, that's, again, a bounded number, and at the end you may or may not find that you matched C, D, E, F, and G as the same node because there was a cycle there. So to repeat more generally, you can follow cycles, but this is driven by an underlying pattern people will expect to find in the data. So if that pattern is 6 or 7 hops long, or regardless of how many it is, it's a bounded number because we don't support regular path queries yet. Because of that, it would just be a fixed amount of computation, and you'd either find something with a lot of repeated matches or you would just not find anything at all after that point. Sorry, does that answer your question? Okay, yes.
Okay.
See me in person.
You were very in time, so there is time for more questions.
So you talk here about the benefits of DFT relative to BFT. What are the downsides of DFT?
Well, if I had to say the biggest downside, it would be that DFT is harder to partition when it comes to actual ongoing work. You have to implement some sort of work stealing or work sharing mechanism for the situations when you have an unusually unbalanced workload, because you'll find that happening more in a DFT than a BFT. Because in a BFT, you can just nicely partition everything because there's a global barrier between the stages. But because you don't see that in this approach, sometimes, yeah, you'll find one thread has a ton of work assigned to it, and then it'll just take some of that and give it to the other threads. It's a little bit of overhead, but as you'll see in the results, we do quite well.
Okay. I think we should thank Nicholas. And hopefully I'll not make any more of those interesting mistakes again. But now you're really on, Martin, with the Gradoop talk.
Gradoop, not web, but there's a, no, there must be another one. Gradoop presentation, this one.
This one?
Presentation, this one.
This one?
Yeah. There a presenter?
Huh?
Do you have a presenter? Thank you.
Great.
Is it working? No. This way. Yeah, hi everyone. My name is Martin. I'm a PhD student at the University of Leipzig. I'm here with Max, who is sitting in the 1 to 5th row, who is a master's student, and together we worked on Cypher-based graph pattern matching during the last 3 months. So motivation, all of you know, graphs are everywhere, and one of the most common use cases is analyzing network of orgs, and you want to know which orgs hate each other. And so the analysts typically ask questions like, who are the closest enemies of each org? So if you want to express this in a graph query language like Cypher in Neo4j, that's very simple. You just do something like that. So you describe the pattern you're looking for. If you want to do this in a graph processing system, like for example Flink Jelly, it looks more like this. So you have a lot of code to write. You have to implement this compute function and to express the same thing. It's getting even more complicated because those graphs are typically not homogeneous like that one, but heterogeneous. So you also have hobbits and clans and different kinds of relationships. And here one typical question an analyst would ask is, which 2 clan leaders hate each other? And one of them knows Frodo over 1 to 10 hops. So if you again express this in Cypher, it would look like, for example, this. So you describe your graph and you have some predicates and you're done. So that's good for the analyst because he's typically not a programmer. So if you do this in Flink Jelly or any other non-declarative graph processing system, the analyst would do something like this. So, and this is why we are focusing on implementing a declarative graph query language on top of a distributed system, like in our case, Apache Flink. We use the Hadoop framework. It's a so-called declarative open source graph data flow system that we develop at the University of Leipzig. And from the architecture point of view, we build on top of a shared nothing system. We use the Hadoop stack, in our case HDFS, for graph storage. We use Apache Flink, a distributed data flow system. Maybe all of you know Spark, so it's very similar to Spark. For operator execution, and Hadoop itself is like an abstraction on top of Apache Flink that gives you a property graph model known from Neo4j, for example, or other graph database systems. And we also implement some graph operators and give you ways to handle graphs from HDFS and write them to other data sinks. So the property graph model is well known in this community, so I don't want to go into detail. What Hadoop does add some extensions here. So one extension is the introduction of so-called logical graphs, which are first-class citizens like vertices and edges, and they can be used to describe subgraphs in your database. You don't have only one graph, like for example Neo4j or any graph processing system. You have multiple graphs, which can also overlap, and they have labels like the vertices and edges, and also can have properties. So, and another extension of this data model is a set of operators which take graphs as input and produce graphs. So those operators are closed over the data model, so you can combine them in a graph analytical workflow. And Hadoop implements a lot of operators, and today we are focusing on pattern matching, and especially on the case on a single graph setting. And let me give you an example. So the input here is a logical graph. You use colors to denote labels. And one could ask a question or looking for patterns like green vertices that point to orange vertices via orange edges. And on the bottom, you see our Java API graph3 is a variable which points to this logical graph. You say .cipher, and the arguments are the pattern query, and more arguments to declare the vertex, the morphism setting for vertex mappings and edge mappings, so that you can vary which are you interested in. So the result here is a graph collection where each graph inside this collection is a subgraph of the input graph that matches this pattern via, in this case, isomorphism for vertices and edges. Okay, graph collection. So on the implementation side, Hadoop provides several graph representations. The one that we use is very relational. So for example, consider our example graph from the beginning. We have 3 data sets. A data set is just a distributed collection of data. It's an abstraction that Apache Flink gives you. It's very similar to an RDD in Spark. And we have 3 data sets here, one for the graph heads. Graph heads store the data associated with graphs. Of course, one for the vertices and one for the edges. So this is very relational. You see that the edges have source and target identifiers. They are directed, and vertices and edges know in which graphs they are contained. And what you see here also is that the properties are stored at these elements. So this is the graph representation, or one of the graph representations of Hadoop, the default one, and this is the one that we are using for our implementation. So our engine is quite straightforward. What we do first, of course, is parsing. So we parse the cipher query. The predicates are transformed in conjunctive normal form. And then we use statistics about the input graph, like label distribution, property distribution, and our reference implementation for our query planner is a greedy planner. And this greedy planner decomposes the query and builds up a query operator graph, which could look like this. And of course, the output is then the graph collection, which is again fed to the user, and you can use it as input for another operator. So let's take this example as this query as an example. So one possible query plan could look like this. Don't be afraid, it's just a debug output, but I want to highlight some details here. So as I said, we decompose the query. So for example, there are operators to extract edges. This is an edge which has the label heights. So there's an operator called filter and project edges node, which does essentially what it's named after. So it filters the edges and projects only those properties that are needed for further processing. So then, of course, there are binary operators, join embeddings node, which join partial matches to larger matches. In this case, this O1 vertex with the heights edge. Then we have operators to evaluate cross predicates, so predicates that span multiple variables, not only one. So for example, like this one here. And for this special case, the variable length path expression, where you're looking for paths from length 1 to length 10, we have this dedicated operator called expand embeddings nodes, which processes exactly this expression. So let me give you an example using those two simple operators. On the upper level, you have the logical view. In the middle level, you have the relational view. And at the bottom is the Flink abstraction. OK, so what we do first is we want to extract only those vertices that are a hobbit and have this predicate through the backends. On relational view, of course, this is just a selection. And we also want to project only the ID in that case. On the Flink level, this is translated into so-called flat map transformations, which we use to implement this operator. So flat map is just a transformation from one data set to another data set, where for each element you can generate 0 or multiple elements, in our case 0 or 1. Another one is join embeddings. So you have two input data sets here. We want to join them on the vertex 01 or the variable 01. And of course, this is just a regular join. And in the join function, which is this flat join function in Flink, we do the vertex and edge isomorphism checks if requested by the user and remove duplicates. And of course, the output is then a single data set containing the joined embeddings, which are then input for the next operator in the query plan. OK, so all in all, if you are familiar with Flink, then maybe this looks familiar. This is just the operator plan, how it looks in Flink. So if you execute this query, this would be something that Flink gives you. And you can read it from the left to the right. On the left, we have the data sets. And then we have the filter operations, join. And this box in the middle are the expand embeddings. So it's an iteration to compute the variable length path. We used LDBC data sets 10 and 100 to evaluate our engine and our 16 nodes cluster. So we have two kinds of queries. One kind are the operational queries with a very local focus. Those are these ones. And operational OLAP queries that focus on the whole graph. For example, this recommendation query. We looked at the speed up, which is quite good for the operational ones, not so good for the OLAP ones, which is due to data skew problems and partitioning issues that we are currently working on. And for the scalability and data size increase, it scales very good. So if you increase a factor of 10, then also the runtimes increase by a factor of 10. So I want to conclude very quickly. I introduced Hadoop, our new operator based on Cypher for declarative pattern matching. It's all implemented in Apache Flink, which also means that you can combine it with our Flink libraries like machine learning, table, and so on. And it's all open source. And if you go to this domain, it redirects you to GitHub, and you can download it, play with it, test it, whatever. Thank you.
Thanks, Martin. If there is a quick question, we can take it. If there is none, then it would be better to handle it at the poster.
Yep.
So thanks. Hubert, please come forward. So now we will see a somewhat related presentation. Although instead of Flink, it uses Spark. But these are very similar, indeed. And it is not about the Cypher query language, but about another graph query language, Spark, the semantic web query language for RDF. Okay.
Okay, good afternoon. So this work is done in collaboration with Olivier Curé from Paris Est University and Bernd Hamann from Paris 6 University in France. So the context is rather the same. So under the impulse of linked open data, we are facing an ever-growing content amount of RDF data that is publicly available. They are, for instance, a large data set with billions of subject property object triples, like DBpedia. To query this data set using a declarative language, we are using a SparkQL. The building block of a SparkQL query is a basic graph pattern. So here you can see two examples of basic graph pattern queries, a snowflake query. You can see the triple patterns with the join variables that connect these triple patterns. And more precisely, you can see the chain pattern. You have 3 triple patterns connected by 2 variables. We will use this example in the following. So Also today there are some cluster computing platforms that are very mature. They provide very interesting features and properties to process large amounts of data. Main memory data management, distributed and parallel data access and processing, fault tolerance, and high availability. So we want to leverage on that kind of very interesting platform, and for instance, Apache Spark. You can see how we can use that kind of platform. So the RDF data is stored in Hadoop distributed file systems, and then all the data is loaded into a main memory, into the Spark platform, in a layer called resilient distributed data structure that does not compress the data. Spark also provides a second layer to store the data in a more compressed fashion, and also Spark provides an SQL interface. So how can we execute a SPARQL query in such a platform? This is our objective to do this. So there are some rather straightforward way to do this. For instance, it's possible to translate a SPARQL query directly into a SQL query and to submit it to the Spark platform. A second possibility is to translate it into the data frame algebra, into a logical operator that is then executed using the optimizer of the Spark platform. The third solution is to translate the SPARQL query into a physical into a physical plan using the physical operator, mainly the select project join operator of the RDD layer. We experimented these three solutions and found that there is room to improve it. So our solution mainly is to improve the way a query is executed into that kind of platform. We assume the following requirements. So we require low memory usage, so it implies no data replication and no indexing. We also require fast data preparation. So here we only use simple hash-based subject partitioning. So a new data set can be very quickly queried. The challenges are both efficiently evaluate parallel and distributed join plans with Spark, that is to favor local computation and to reduce data transfers. The benefit, also the other challenge is to benefit from several join algorithms, because in that kind of platform there are three join algorithms. There is a local partition join that process locally without transfer. There is also a distributed partition join that is a kind of parallel hash join. And there is also a broadcast join that is a kind of distributed nested loop join. The solution is twofold. First of all, for local subquery evaluation, we propose to merge multi-triple selection into only one selection. This is a well-known solution called shared scan. And also we propose for distributed query evaluation, we propose a cost model. So we devise a cost model specifically for partitioned and broadcast join that takes into account the data transfer and also the selectivity of a triple pattern. And then we generate a hybrid plans that combines in a bottom-up fashion the join operators to build the plan. So here you can see the example of the first slide. So this is a rather simple query with 3 triple patterns and 2 joins to perform. So suppose you want to use directly the RDD layer of Spark. This will end up with that kind of plan. So this is the optimal plan using only the partition distribute join. You can see that the result of the triple pattern T2 is distributed over the cluster. So the first join is performed. The triple pattern T3 does not need to be distributed because it is already partitioned by subject, which is the join variable. And then this sub-result is also distributed to get the final answer. Using the second layer, which is the data frame layer of Spark, the optimal plan would be to do a broadcast join. So the query optimizer of Spark understands that the result of T2 and T3 are rather small, so it is better to broadcast them through the cluster and to process that query. there is something. What is it? But hopefully, however, these two plans are not optimal. A better solution would have been here to first benefit from the small size of T3 to broadcast it, to do the first join, and then to only distribute the T1 result to get the final result. So using our cost model, which is rather simple, it only takes into account the size of the triple pattern and also of the intermediate result, and also the number of compute nodes, we can get that final plan. Here, we compared with state-of-the-art solution to process Sparkle queries using Spark. This is a VLDB paper published last year. So we are using the same benchmark from the Waterloo University with a 1 billion triple dataset. And what is important here to see is, first of all, we did 2 experiments. So if the dataset is, if all the triples reside in only one dataset, so this is the comparison between the blue and the purple curve. So you can see that there is a benefit of 2 times here. But more interestingly, we're using the same partitioning as the S2 RDF competitor. They are partitioning by property and by subject. So we can achieve a 2 times better response time. So interestingly, this approach can easily combine with what is proposed, because in this approach they do not study how to use a different kind of join algorithm. So they were more concentrated on partitioning the data. So here it would be possible to improve their result. Okay. So to conclude, so it is possible to exploit existing computing platform to process Sparkle queries at a very large scale. But this requires to accelerate query plans. There is room for improvement. That kind of platform are rather generic, and although they can easily process Sparkle queries, it is better to explore several algorithms to execute such the join algorithm in this platform, and also it allows for mixing several join algorithms. Thank you.
Thanks, Hubert. Do we have a question? Yes.
Did you consider implementing your Sparkle engine on top of GraphX?
GraphX, as it was explained in the previous presentation, is more dedicated for iterative exploration of a graph, and it would result in a very long expression. The GraphX does not have a query processor. GraphX is more, as I understand GraphX, maybe you are familiar with GraphX. It is more to do like some PageRank search.
It is similar to Giraffe in the it's like a BSP library, Pregel like. So yeah. Understand. But another competitor would have been like other RDF stores, like for Virtuoso, for instance. Have you considered? Have you compared with like standalone Sparkle processors?
Compared with solutions that do not rely on Spark?
Sure. Yeah.
Yes, there are many solutions that many dedicated RDF query engine, and at the moment I would say that it is not as efficient as this dedicated engine, because they are indexing the data a lot. They are often they do not store the triples like that. They are indexing by subject to object, subject to property, and they are doing all that kind of indexing. So it is a rather long data preparation time. So you will lose in preparation time using that kind of system, but after the query are very fast.
In those competitor systems, you mean? Yes. They don't. They use a lot of indexing.
They are using extensive indexing and also replication sometimes. I would say the most related competitor in that kind of work is RDF Fox that is now distributed also. But they implement their own distributed framework, and so it's also a lot of work to re-implement all that distributed query processing instead of using.
Right. Okay, we have to cut it short here. Thank you, Hubert, again, and
thank you.
We will now give the stage to Dean de Leo, who will talk about extending SQL with shortest path functionality.
That's right. Yeah. Please. Sorry. Yeah, okay, sorry. So, hi, my name is Dean de Leo, together with Peter Bones. We are here to present a proposal to extend SQL to compute shortest path queries. And so the problem is, suppose you have a graph where nodes and edges can have arbitrary properties. We want not only to have a way to compute the shortest path between a source and a single destination, but between different combinations of vertices. But we rely on an additional property that before answering whether there is a shortest path between two nodes, we ask whether those two nodes are actually connected. And this is a reachability problem. And even a more fundamental problem is that what's a graph in terms of the relational model or in SQL. So in this presentation, we are going to address these points in the reverse order I introduced. And then we have a prototype implementation in terms of on top of MongoDB. I'll give you a quick result to show where we currently are, and then I'll conclude. So for the graph representation, usually many solutions adopt, several solutions at least, adopt the view, you have an edge table where you represent all the edges with the properties and a vertices table with all the vertices. In our proposal, we just say, we are kind of in the same trail, but we just say, well, you don't really need a vertices table formally, because once you have the edge table and you decide and you define which are the sources and which are the destination attributes, then the vertices can be implicitly derived by the set union, the projection of the source and destination edges. However, there is a gotcha. If you also want to represent properties with the vertices, you need an additional table, and you're back to the situation of the entity relationship mapping. And so for our purposes, a graph is given by the edge table. The first point we are going to address is that how we address reachability. So this is a predicate, and we introduce a new clause in our proposal, a search predicate. And the point is that the main point is that the main peculiarity is that besides referring which are the source and destination, you also need to specify to which edge table it refers, and this is a table reference. It's worth to stress that when I talk of table reference, edge table, these are like table expressions. So they are not statically defined, but you can construct during the SQL query. And the other point is that when you put a search predicate instead of aware context, you basically filter out the tuples. And for shortest path, instead, we require that a reachability predicate is already present. And if there is, we introduce a special function we call cheapest sum. The result is, you have two new components, which are the cost and the path on the graph. But it takes two additional arguments. One is a numeric expression, which you want to bind to the underlying graph, and it's the way you express weights, so to compute a weighted shortest path. But the other important argument is a binding variable that you actually, which is the mean to associate to the underlying edge graph, so to the underlying graph, so to the underlying edge table, which comes from the reachability predicate. And the final point is how do we represent a path? So a path, in theory, is a sequence of edges. But from the other point, we want to preserve the semantics of a projection, where you can introduce new components, but you cannot introduce new tuples with respect to the input relation. So in our proposal, we say, OK, you can represent a path through a nested table. And a nested table is basically, it's not present in these terms in SQL, but it's supported by different vendors with different ideas, to be honest. And in SQL, in standard SQL, you actually have the concept of collection types and row types. So you can get away with these terms. And the final point is, OK, once you have this nested table representation, how do we get back to the actual tuples? Here, our proposal already ended at the previous slide, but what we say is that we rely to an existing operator, the existing SQL, that is a nest, and what it does is basically expands the nested table with respect to the tuple that contains that component. So given the sample, it does this expansion. As I said, we have a prototype implementation on top of MongoDB. So this is an early result. We coming from the 13th query of the LDBC NCB interactive workload. And what happens is that in our current implementation, we always materialize the whole graph. And this has a significant cost. So, and we can get away with this cost. We can only amortize when you perform a batch when you ask multiple shortest path queries, which is what this graph shows. To conclude, here was a presentation of an extension to SQL to compute the shortest path. We are in the problem of the many-to-many shortest path. Our current stage, we are improving our implementation because of this materialization cost. But what we are actually looking for the future is to have a way to express or to pre-compute the graph in a materialized way, even being resilient to updates and to the transaction mechanism that databases should support. And that's pretty much.
Thanks, Dean. You were very much on time, so we do have time for a question, and I see some raised hands. Marco.
Hi, really nice talk. 2 questions. First, you assume a fixed data schema, right, for that?
I beg your pardon?
A fixed data schema from the relational system to be able to
no, that's actually one of the advantages, is that you construct the edge table. We say it's a table expression. It can be constructed by the composability of the SQL, and you create a runtime.
Okay. And another question is like, what SQL implementation you assume that at least the underneath system has? Is ANSI 99?
So the only tricky point we are assuming from SQL are these collection types that are the way that we represent nested tables. Now, collection types started to be described in the standard from SQL 99, but they weren't quite that. So they are completely described in SQL 2011, which is the reference we used to prepare.
There was another question.
So I wanted to ask you about the motivation for making such an extension, as opposed to the motivation of representing graphs in databases, which exist. So just the question of why would we as a community want to have this in the SQL standard, especially considering how many DBMSs don't implement the entire standard even now?
Right. So this is so from one side, why to implement in SQL is because there is currently there is an increasing interest on graphs from the community, and there is an increasing pressure to have graph processing in SQL. This doesn't answer the whole plethora of graph processing, but only one specific problem. And compared to different languages, it's because SQL is almost an ubiquitous language that is used for data manipulation, and it's well known, instead of introducing a new language that has to be implemented.
Okay, so with that, I think we have to cut you short, Dean. Thanks again. And it's time for me to introduce Frank Tetzel from Dresden, who will talk about graph compression. And this will be our final talk. We are slightly late, but I hope you bear with us.
Okay. Hello, my name is Frank Tetzel, and I want to talk about the feasibility of graph compression for indexing regular path queries. So first, kind of a refresher, what are regular path queries? Regular path queries is for matching paths conforming to a regular expression. So we are not just interested in matching single edges, but we want to match complete paths, and sometimes also on unlimited length. Of course, in the data graph it's limited, but we kind of don't know upfront what is the length. And the result out of that is only kind of a set of distinct pairs, start and end vertices, which have at least one of such a conforming path between them. So it's a reachability query in the very end. So one way to evaluate such a query is to convert the regular expression to an automaton, and use then this automaton for guided search on top of the data graph. And then we, in the end, get just a final result set, which is just this set of vertex pairs. But one problem is that the result size can easily explode. We can imagine if you have a regular expression with unlimited path length, we can find many of such paths in the data graph, and it can easily explode. So one idea was to, because it's just the reachability information we have in the end, we store this reachability information as an index and then later retrieve that. So in this paper, we only did an empirical study with this index, with this materialized reachability index, and we compared two things. So one is the baseline, doing the guided search as I just described with the automaton, on top of a column store. And this column store just has a vertex table and an edge table, and because we don't want to do a self-join on the edge table all the time, we have an adjacency list kind of as a neighborhood index, so that the traversal is sped up by that. And we compare that to what we call an MR index, which is just a name for materialized reachability index, which stores the final result set of the RPQ for future use. And we treat the vertex pair we get out as an edge in a reachability graph, and we want to store this reachability graph, this final result set, with the normal graph compression which are available. And the graph compression scheme we investigated was a K-square tree, and it's kind of fitting nicely to that because it's a compact representation of a binary relation. And this reachability, what we have in the end is binary. Either two vertices are reachable over the conforming path with the regular expression, conforming to the regular expression, or it's not. So we kind of, this fits nicely into that. And if you look at this reachability graph with a kind of thinking about it as an adjacency matrix, we have this here as an example, and if you have an edge between two vertices, we have a 1, and if not, it's a 0. And this K-square tree now works in a hierarchical way, similar to a quad tree, and if this k is a parameter here, and if we set this k to 2, we split the binary relation, in our case the adjacency matrix, in 4, so k-square submatrices. And we look in each submatrices, is there at least one edge in this submatrix? Then we represent this whole submatrix with a 1 in a tree. If there's no edge in there, then we represent it with a 0, and we prune then later. So kind of here's this uniform 0 region, and we represent this with a 0 in the tree, and then prune the whole tree below it. And we recursively continue that, so we split all the 1 regions where there's at least one edge in. We split it again in 4 submatrices and do exactly the same. And the order in the tree, how we order the submatrices is in Z order. So we start in the top left, then to the right, and the bottom left, and then to the right. And we continue till we reach the leaf level. And this tree is also just conceptual. So in the end, we store that just as a set of bit vectors. So in our case, because we use the hybrid k-square tree, so where we can change the k per level in the tree, we split that up that we have per level also a bit vector. So these T1, T2s are the inner levels in the tree, and just concatenated from left to right. And then we have also on the leaf level, we also have one concatenated bit vector. And for this leaf level, we can also do then some more compression just on this bit vector, which is then a leaf compression. So what we did then, we looked at the LDPC dataset generated with scale factor 1, and then also generated all possible RPQs, which have at least one result. So we took the LDPC schema, which is behind the social network, and looked for all possible paths up to the length of 3, and then recursions of that. And in this case here, we partitioned each of these queries into how big is the final result set, how is the selectivity there, and we looked at the runtime. And what we can see here, it's fluctuating quite heavily. It depends on the intermediate result set, and this is very different per regular path query. But in the end, what we can see is that our index is most often smaller. So this index is either the k-square tree or the k-square tree with leaf compression, K2C, or we just store the final results as just an adjacency list and not compressed. And we see at the very end, if the result set is very, very big, we have a problem with extracting the result from the k-square tree. So that's why we see this peak there. If you look at the space consumption, then we see that, again, we have that in the x-axis, the selectivity. We see that the k-square tree or the k-square tree with leaf compression is way smaller than just storing it in an adjacency list. So that's the main benefit here. Another measurement we did is we looked at batch processing. So we had a batch of 300 queries, randomly selected from all these queries we generated before. And then we have a memory budget, so in this case 10 gigabyte. And we looked what is fitting in this memory budget. Then we took the index for that. And if it's not, we have to do the baseline, the normal guided search. And as we can see here that the k-square tree, because it's so small, the indices, we can store way more and extract the results out of that. So the combined runtime for the whole batch is way better than just doing the baseline. And we also did a very simple greedy algorithm, this is this best case, which picks basically from each variant from the adjacency list or the 2 different k-square variants, the best for each query. To conclude, we found that graph compression, in our case the k-square tree, is quite good for storing reachability information, but it has some problems. If, for example, the result set is too small, then it doesn't make sense to store it compressed. And if it's too big, then we also have a problem, because as we saw, if you don't have these uniform 0 regions in the adjacency matrix, then we cannot compress that. But there are other variants of k-square trees where we can also compress 1 regions, but we have not investigated into that. And there's also the possibility to do range queries on k-square trees, which would then speed up the extraction of the result sets of out of the K-square tree again. So that's something to look at. And also, what would be nice to compare against this other reachability indices like Ferrari, which is a compact reachability index, or other graph compressions. We did not investigate into that yet. So that's all. Thank you.
Thanks, Frank. Last opportunity to ask questions, at least in this room. Is there anybody?
So I guess I'll ask what the K stands for in K squared.
I don't know, that's just a parameter. I didn't invent this data structure, so I cannot tell. So this is just K. They just chose K as a parameter, and you can set it in the hybrid K-square trees where you can set it per level. I don't know what the K stands for. So in this case, if you set K to 2, it's very similar to a quad tree, if you know that.
Mm-hmm. Yeah. I have a question myself. So if I understand correctly, this K2 index compression is useful for any kind of for encoding any kind of graphs. So you can create any kind of index with this. So RPQs, but also something reachability of RPQs, but also other stuff, I suppose.
Yeah. So actually, it comes from normal graph compression. So for web graphs, actually, the first time they did it for web graphs. But the problem here is it's because I said binary relation. So for multi-graph, you have the issue that you can have multiple edges between two vertices, and that's kind of not possible to represent here. There is a paper about that where they extend that for property graphs, also including multi-graphs, where they basically do some auxiliary data structure to deal with multi-graphs and also with properties. So there are a bunch of variants where you can store different things there. Yeah.
We see. Okay. Well, if there are no more questions, then I would like to thank Frank, first of all, again. Well, and I would like to thank all of you for being here and for sending interesting paper submissions to grades. And would like to close with the final plug. So if you're interested in LDBC things, so benchmarking of graphs, then likely indeed the next meeting of LDBC would be in Munich at VLDB on the last day, also on the Friday. That's September 1st. So these meetings are, well, they are slightly more geared towards slightly more geared towards LDBC benchmarking, but they're also open. You don't need to be a member of any, so you're definitely welcome. And yeah, with that, I will not say the workshop is closed because there is a session where we have the opportunity to further discuss now that you've seen all these presentations. Please ask questions at the posters, and we'll have roughly an hour for that still. So thanks again, and well, we'll see each other in the poster session. Bye. Oh, somebody found this card of the SX Inn. This is a room card. Don't know which room number. It's not mine. Mine has a different drawing on it. Who is missing the hotel card? You can. Well, if it's missing, then ask me. I have it. It's yours?
I brought one and I don't have it, so it's
And this is it was like.
very nice.
I'll go there to the poster of it.
That's what I understood. Of course, it's an error, yes. Historical.